Right then, so today we're going to prove that root 2 is irrational. And we're going to do this by using proof by contradiction. So we're going to start straight away and we're going to start with our assumption. So if we're trying to prove that root 2 is irrational, we're going to first assume that root 2 is a rational number. So it lies in the set of rational numbers there. Then this means then root 2 is going to be equal to a over b for a and b, which are both integers, and note that b cannot be equal to 0 since b is at the bottom of the fraction. If it was equal to 0, then it would just break mathematics, and we don't like that. So we also have to say, and a and b have no common divisors. So this means that this fraction a over b is in its simplest form. So nice, right? So to prove that root 2 is irrational, we're going to have to first prove that this statement here is incorrect. So the way we're going to do that is we're going to use this statement here. So we're going to have root 2 is equal to a over b, and then we're going to square both sides of this. So we're just going to have I'll do a little arrow there. So we're going to have 2 is equal to a squared over b squared. Then we're going to multiply both sides by b, which means we're going to have 2b squared is equal to a squared. Right then, and since up here we defined b as an integer, so that also means b squared is going to be an integer. And that means we've got an integer that's been multiplied by 2, which is going to equal a squared, which is another integer. So if a squared is equal to 2 lots of b squared, then that means a has to be an even number, because no matter if b squared was even or odd, if it's been times by an even number, it's always going to give us an even number. So this means that a squared is an even number. Right then, so there's a nice little place, just take a little break, and we're going to have a little note here. So this is going to be, it's like a proof within a proof. So this little bit here, and now a lot of people, when they do this proof, they just assume that if a squared is an even number, then that means a must be an even number. But I'm going to go a little bit further. I'm just going to prove this as well. So I'm going to do this by using this little note here that I'm making. So if n, so I'm just going to use n instead of a, is an integer such that n squared is even, then n is even. Right, so the way we're going to do this, we can't really use contradiction. Well, actually, I don't know if he could or not. He might be able to, but I know another way which is better, and we're going to use proof by the contrapositive. So the opposite of this statement, note that it's not, I know it sounds quite similar, because like you could say that, oh, the opposite of this statement is this statement, and say that contrapositive and contradiction are very similar, but they're not. Well, I mean, they are similar, but they're still different. So we're going to use the opposite of this statement here that we just wrote, and we're going to prove the opposite correct, which then means that this is true. So that means equivalently, we can prove that if n is an integer and n is odd, then n squared is odd. So this is a proof by contrapositive. Right, so that's the opposite of this statement, but because we know if we prove that if n is odd, n squared is odd, then that would leave all of the even numbers left, and that would mean that all of the even numbers would then have to equal a even square if you squared it. So we can then write that if n is odd, then n can be wrote as 2k plus 1, where k is an integer, like that. Therefore, n squared is going to be equal to 2k add 1 squared, which then we can expand these brackets here. So we're going to have 4k squared add 4k add 1, which then is going to be equal to, I'm going to take out a factor of 2 here just to make it very clear that this is a odd number. So here we go. We've got, since k is an integer, then, oh, that's a dodgy z. I didn't just realise that. There you go. Since k is an integer, that means this whole, oh, not even added the 1. There we go. Since k is an integer, that means this whole bracket here is going to be an integer. We're times in an integer by 2, and then we're going to be adding 1. So n squared is odd. Therefore, n squared is odd. Right then, that is lovely. So that is our little note there. So we have just proven so we've proven this statement, and in turn we've proved this statement there. So now we know that a is even. So if a is even, then a can be equal to 2m, such that m is an integer, which is quite nice. So that means that we can then use the equation we got up here, where it was 2b squared equals a squared, and substitute that in. So we can have 2b squared is equal to, now since a is 2m, we can have 2m all squared, which means that 2b squared is going to be equal to 4m squared, which means that b squared is equal to 2m squared. And since m is an integer, that's been times by 2, that means b squared must also be an even number. So this means that, so b squared is even, therefore b is also even. This means that if a and b are both even numbers, I'll write this down actually. So a and b are both even, they can both be divided by 2. If they can both be divided by 2, that means they do not have they do have a common divisor. They do have a common divisor. That's poor English. Anyway, yeah, so they do have a common divisor, which up here we assumed that they have no common divisors. So that means we've got a contradiction. So we've contradicted this statement, this assumption up here, which means that we've proved our original statement that root 2 is irrational true. So we can say that we can conclude that root 2 does not lie in the set of rational numbers. Lovely, and that's it.